Okay, so before we get into the actual content of our lesson for today, I want to talk just really briefly about what I did with the section here. This topic on blocking and experiments is technically part of section 4.2 still, but I took this piece of the section and I kind of pushed it back so that when I give you guys a quiz over 4.2, blocking will not be on it. So at the first time you guys are watching this video for me in class, we will talk about just one quick thing in these slides that'll help you guys review for general completely randomized design experiment stuff that'll get you ready for your 4.2 quiz. So I would expect that the first time you're watching this, it'll be for like the first 5 minutes of the video, and then you can revisit this and watch the whole new lesson later on for the next class period. So anyway, the thing I want to talk about in this first part here, for the first time you're watching this, is introducing this problem right here and talking about how we would use a completely randomized design as an experiment. So remember, completely randomized design is just a general experiment like you would probably think to do, where there's nothing fancy going on. Blocking, which is the subject of this lesson, is like a more sophisticated or fancier way of running an experiment. So the context for this problem is that we have 20 students available, and those 20 students have taken the SAT before, and they're going to participate in an experiment with an online and an in-class prep course for the SAT. So we want to see if these kids are going to do better with their SATs if they're either in an online class or an in-person class. And we need to describe a completely randomized design to get this done. Now, I've done this a couple times with you guys where we've made a little experiment diagram for the randomized design, but I want to show you, because I haven't done this in a lesson video yet, how you would actually describe this with like a little list. Because if the AP test asks you to do a question like this, you're generally going to want to do it via like just description rather than having to make a picture. So pay attention as I go over this, because your 4.2 quiz will have a problem where I ask you to design an experiment like this and use a completely randomized design. So I've got 20 students at my disposal, and they need to go to online and in class. Those are going to be my two treatment groups right here. So the first thing I'm going to do, you can do it where you put everybody's name on an index card and shuffle those up, or you can give everybody a unique number. I'm going to go ahead and do it the number way, although either way is cool. So assign each volunteer a unique number from 1 to 20. So everybody has to get a number first. So unique number from 1 to 20. When you specify this, make sure you're saying unique, which gets rid of like the technicality of, oh, I gave somebody the same number twice. So everybody gets a unique number here. After I give everybody a number, what I'm going to do is use randint on my calculator, or use some sort of random number generator. So randint, the command would be 1, 20. I'm going to pick a number from 1 to 20. And I'm going to do this to generate 10 unique numbers. Again, I'm specifying that the numbers are unique, which means that there are no repeats allowed. It's always a good thing when you do problems like this to explicitly say if repeats are allowed or not. Here, I definitely don't want repeats. I wouldn't want to pick the same person twice. After you talk about how you're going to pick your 10 people, didn't give myself nearly enough space here. The next step is going to be to say what you're going to do with those 10 people. So those 10 people, the 10 people corresponding to those numbers. So the 10 people corresponding to the selected numbers go to online class. And the remaining 10 to in person. It doesn't matter which 10 go to which group as long as the selection of the 10 was random. So if you would reverse the order of this, that would be totally fine as well. So they go to the class, they take their class. I'm I'm running out of space here, so I'll delete this when I continue with my video. But the next step in my process, I would have to give them the SAT. So they take their little class. After class, have subjects take the SAT and measure their improvements. Okay, so they take the class, they retake the SAT again, we see how they improve because everybody's taken it before. The very last thing you have to do when you talk about an experiment is talk about what happens with your results, the comparison step. That's really, really important that kids tend to forget. So my last step in this process is going to be to compare the improvement scores between the two groups. So when I ask you to design me a completely randomized experiment, you need to talk about labels. How do they get their labels? So I said assign each volunteer a number from 1 to 20 that's unique. Talk about how the randomness takes place. It could be if you're shuffling names out of a hat, doing that. It could be talking about randint with repeats or no repeats. Then you need to talk about what happens to the people once you've randomly selected them. So where do they go? What do they do? Talk about the experiment itself. Oh yeah, collect data, blah, blah, blah. And then talk about a comparison at the end. You're going to compare your two groups. So this is what I would expect to see when you are asked to design a completely randomized experiment. I'm going to go ahead and delete this, and I'm going to continue with the video right now. But if you haven't had your 4.2 quiz yet, this is where you should stop for now. I'm going to carry on, though, and you'll pick up from this point in the next lesson that I assign you. All right. So I'm talking to you in the future now compared to when you first watched this video. This is where you pick up to talk about our new concept of blocking. So what we just finished diagramming right there, it was just written on the screen, is an example of a completely randomized design. But the issue with this design, in our little fictitious problem about the SAT, it turns out that out of those 20 people who volunteered to be in our study, they were in different math classes. 10 of the kids were in pre-calc, 6 were in algebra 2, and 4 are only in geometry. What kind of a problem would this cause in terms of SAT scores and the value of this class? So think about that for a second and hopefully come up with something in your head. The biggest thing, I'm telling you the answer now, the biggest thing that this would cause is, depending on how much math you already know, this class probably isn't going to be as valuable if you don't know as much. Okay? If I put a third grader through an SAT class, it's not going to help them at all because they just don't know enough math, that it's not going to make sense anyway. If I put somebody in pre-calc through this class who already knows the stuff and may have forgotten things, the review is going to be really beneficial, and I would expect the pre-calc kids to benefit more than the geometry kids who haven't learned those tougher things like logarithms, etc., etc. Okay? So going in, the amount of math you already have learned in the past is probably going to have a pretty significant impact on how much this class actually helps you. So the amount of math you know, you know or you have learned will have or could have a major impact on how much a review class helps. Again, if you've never learned the content in the first place, seeing it in a quick review SAT class isn't going to make you understand it well enough. You have to have been in the content and seen the class for real. So that is not really an ideal thing right here, because those pre-calc kids may end up just getting way more out of this class than the other kids, and that could make things trickier when we're actually analyzing our results. One way to solve this problem, the best way to solve this problem, is to use a concept called blocking. So blocking is a different type of experimental design as opposed to a completely randomized design, and that is what I need to teach you about in this lesson. So let's go on to the next page and I'll explain what blocking actually is. So a block, as a general vocab term right here, a block is a group established by a researcher with a common characteristic. And the big thing about a block is that it's established before you do random assignments. Okay, so a block is established before random assignment. This will make more sense when I actually break down this problem, and I'll show you how it works. But a randomized block design is an experiment involving, this is a bad definition right here, but it's an experiment involving blocks. So how would this work? Rather than have all 20 of my people and be like, oh, random assignment, 10 here, 10 here. If I do that, it could be that I just end up putting most of the pre-calc kids, like what if 7 or 8 pre-calc kids just magically end up in one group by random chance, and the other group only has 2 or 3 pre-calc kids? Well, this group with a lot of pre-calc kids is just going to look really good. Maybe if it's online or in person, it could just be the fact that they're in pre-calc that's making this group look better than this one right here. So what we do, if we're pretty confident that math class is going to make a difference, we take each group separately. We take our pre-calc kids, all 10 of them, and then we would divvy them up. So like randomly assign 5 to each group. There were 6 kids in Algebra 2, randomly assign 3 here, randomly assign 3 here. So rather than relying on just my big pool and hoping that they end up about even when you deal them out, you break them into little piles called blocks. And then from those blocks, what you do is you randomly assign parts to each. This is actually a lot like stratified sampling. So this is a concept that kids sometimes confuse with stratified sampling. The big difference with stratified sampling is that you are sampling. It says it in the name. When you sample, you pull out of the population. So again, my prom example, I have freshmen, sophomores, juniors, seniors. I'm sampling people to be in my study. So I would pull from the list of freshmen. I would pull from the list of sophomores. With blocking, let's say I was doing an experiment based on a school somehow, and I wanted to make sure I got some freshmen to each group. I am assigning, putting into groups rather than sampling and pulling in. But it's a very similar concept here. So creating a diagram outlining this problem with our randomized block design for SAT, we would start out with our 10 pre-calc kids. That would be one block. We would have 6 kids who are in Algebra 2. And then we have my little toolbars in the way here. I got 4 kids who are in, that does not look like a 4 kids in Geo. And then what you're basically going to do is do a very similar process. I'm not necessarily going to write this whole thing here, but what you would do is you would randomly assign it so that 5 of the kids end up in each group. So you would have 5 of the kids go to treatment 1, which is, I don't know, the online class. And then you have the remaining 5 go to the in-person class. And you would have the same sort of deal with the Algebra 2, except this time there were only 6 of them. So you'd have 3 and 3. So that way you're basically making sure you have 5 pre-calc kids in each group, 3 Algebra 2 kids in each group. And we'll talk about why this is beneficial as the lesson progresses here, but that is what blocking essentially means. Now, one more thing, because I'm not writing this whole thing out here for my experimental design, but after you get your results, so after they take their class, blah, 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 when you make your comparison, what you're going to end up doing is comparing within the block first. So compare within the block. What does that mean? Basically, when you get your results, compare apples to apples. pre-calc kids versus pre-calc kids, algebra 2 kids versus algebra 2 kids. You compare those different parts of the same block to each other because that is more likely to tell you if something is really going on. So let's keep things going in our lesson right here. And what I have on this next slide, I'm pretty sure, yeah, it's like hypothetical results for what actually happened in this study. So the kids took their classes, life was good. And then what we did is we went ahead. I think they did use blocking in this. Yeah, so this was with blocking. So if you count it out, there are 5 pre-calc kids in each group, 3 algebra 2 kids in each group, 2 GO each group. And this shows when they took their SAT again, hypothetically, what their results ended up being. So we need to make ourselves dot plots right here, side by side, so we can look at our results. Our whole next chapter we will talk about is all about graphs and what they're good for. But when you look at this, it's kind of hard to tell if one is necessarily better than the other. So I'm going to go ahead and graph these on top of each other right here and see what's going on. So I'll start at 0, 10, 20, 30, 40, 50. And you guys should be graphing these as well. So while I'm just talking here, you can start making your own graph. I don't know why I started numbering all of these. So yeah, make your graph and try to make them stack on top of each other, because when you do it that way, it'll be easier to see if there is a difference between the groups. We talk about overlap in the pictures, and we did that in the previous lesson here, so that should be a little familiar for you guys. I'm going to make my first group, this will be the online group, and this will be the classroom group. And what I'm going to do is put a dot for each kid where they end up. So pre-calc kids start out with online. I have 2 kids who got 100 point improvements. That's good, etc. So go ahead and graph them and make sure you put them on the appropriate axis here. So 90, 90, and another 100. Those are my pre-calc kids. Then it switches to pre-calc in the classroom. So I have 70, 70, 80, 80, 80. All right, so that's pre-calc. Algebra 2 online is 50, 60, 40. 50, 60, 40 is right there. Okay. Algebra 2 in class is 34 to 20. And then GO online 30, 30. And then GO classroom 0, 20. Okay. So you guys should have these graphed on your own here. And then what we're going to do is look at these pictures and try to decide, is there compelling evidence that the online class is better than the in-person class, or vice versa? And we will learn much more sophisticated ways of doing this using like actual statistics later on, primarily second semester. For right now, we're just kind of using our gut and we're looking at the picture. And the key, like I told you, is overlap. If there's a ton of overlap between the two groups, the results aren't compelling enough for me to be like, wow, there probably actually is a difference. There could be just a small difference. If there's only like a very small difference between the two groups, I could assume that difference, or I could suspect that that difference only occurred due to the chance of the random assignments. So if you look at these two pictures here, that's what I care about when you compare dot plots, is the overlap. And if you look at the bulk of these points go from here to here. These points go from here to here. These points right here have an awful lot of overlap to them. There's a very strong amount of overlap right here, where if I was looking at this picture, yes, the kids at the end, nobody got a 90 or 100 at all in the class group, but I have 5 kids who got it in the online group. You might be like, online can be a little better, but there's so much overlap between the two groups that this probably isn't enough to be convincing, okay? So what I'm gonna write here, just informally, I'm gonna say there's too much overlap to be confident of a difference. If I was writing this as like a full free response question, I would say there's too much overlap between the scores. Context is really important. Too much overlap between the scores. We can't be confident that one class is necessarily better than the other, okay? So when your data is spread out, that's a lot of variability. We've talked about that before. Variability is not our friend in experiments because when you're more spread out, it's more likely you're going to have that overlap and then your results aren't going to be convincing. Okay? I need to erase this picture, I think. Let me see if I can keep it here actually. When I tab to my next slide. Okay, it's a little bit of a mess right here, but this is important and I want you guys to see what's going on. When we made our dot plots by hand, we kind of like threw out the fact that kids were in different math classes. Like you might remember, oh, those kids I think were in pre-calc, but it's not very evident by looking at these dots right here that they're in different math classes. We kind of disregarded that. So what this picture did is it took that same data. You can see the shape of this graph is the same, although their classroom and their online are reversed from mine. I should have looked at that ahead of time. So be aware that this matches up with here and that this matches up with here. But you can see that the shape of the graph is very much the same. All they did differently, instead of dots for everybody though, is they put different symbols for each math class that the kid was in. So our pre-calc kids are the triangles right here. Our algebra 2 kids are the gray dots, and then the squares are the geometry kids. Here is why this is actually more beneficial. If you look at the groups individually, earlier in this video, I said the whole point of blocking is that you're comparing apples to apples, oranges to oranges, etc. But when I looked at my graph right over here, I didn't really do that. I just looked at everything as a whole. Look at the groups individually. So if I look, here are my pre-calc kids for in-class. Here are my pre-calc kids for online. No overlap between those groups. This group is all higher than all of these kids right here. If this was just random assignment here, it's very unlikely that every single kid would beat every single kid right here. So what that tells me is, man, that online class might have actually helped. Same thing when you look at Algebra 2. Granted, there are less dots, so not great making conclusions based on 6 data points. But there's quite a bit of separation right here, only a little bit of overlap where these two kids tied. And then with the geo, I got this versus this. So when you look at the groups individually, apples to apples, it becomes a lot more clear that the online class in this scenario was better. It appears that online led to higher improvements within students of the same math class. So out of all the pre-calc kids, the kids in the online class did do better, and same with Algebra 2, and same with geometry. So when you actually look at the blocks and compare within the blocks, apples to apples, it becomes easier to see if your results could be statistically significant, where things get cloudy when you look at the data overall. So this is kind of a visual demonstration of why blocking is helpful. It helps us determine if things are statistically significant or not by accounting for a source of variability in our data. So that was a big mouthful right there. Source of variability in our data is what math class you're in. Depending on what math class you're in, that's going to swing how much you improve in this class quite a bit. Well, if you kind of take that off the table and you balance it out, so you've got this versus this right here, all pre-calc, then you don't have to worry about that clouding your results anymore. So it accounts for a source of variability in the data. I'm going to have you write that at some point in the slides, but I want to see if I did that elsewhere. So what I want to do right here is show you guys just a quick way that you can, this is an alternative kind of extension sort of a deal to just a straight up block. There is another way that we could kind of put everybody on the same playing fields. So what they did, if you look at this right here, because this is going to take a little bit of explaining for you guys to understand. It says right here that the average improvements for students in pre-calc was 86. I'm going to start right there. So if you take all those numbers right here, 100, 100, 90, 90, 100, 70, 70, all those pre-calc kids, and you average their scores together, turns out that average is an 86. So no matter online or classroom, everybody together who was in pre-calc improved by an average of 86 points. Okay. In Algebra 2, so if you add up all these numbers right here for the Algebra 2 kids, those numbers average out to 40, and Geo averaged out to 20. So another option, this is like kind of a just above and beyond sort of thing that you can do. If you are in pre-calc, your score is expected to improve by 86 points just by virtue of being in pre-calc. That's just the average of everybody in pre-calc. Okay. So this is kind of like the head start or the bonus or whatever that you get, the benefit you get just from being a kid in pre-calc. What we do a lot in statistics is we analyze the difference after you account for things. Like we do a lot with differences in statistics. So in this context, what I'm going to do is I'm going to take each of my pre-calc kids and I'm going to subtract 86 points right here. So if I subtract 86 from this, I wish I had written these out ahead of time, but that's a 14. That's a 14, 4, 4, 14. And then we have negative 16, negative 16, negative 6, negative 6, negative 6. Okay? So this is these are the numbers after we take out that average improvement of pre-calc kids. I'm going to do the same thing with Algebra 2. But by being in Algebra 2, your score improved by an average of 40 points across the board. So by being in Algebra 2, this is like your Algebra 2 bonus right here. So if I subtract out that, I get 10, 20. So I'm subtracting 40 each time right here. So I have negative 10, I have 0, I have negative 20. And then with the Geo kids, I have a minus 20 for each of them. So I should change colors again. And then I'm going to have 20 points subtracted off from each of them. This is going to end up being a 10, a 10, a 0, that's negative 20, and a 0. So what this did is it basically leveled the playing field in a way by removing the advantage of being in that class, so to speak. So these ones got 86 points knocked off, these ones got 40 points knocked off, and these got 20 points knocked off. Now that all the kids are more or less on the same playing field and we eliminated the advantage to being in a certain math class, what we could do now is we could look at all of our online kids. So these guys are online, these guys are online, and these guys are online. And we could graph all of these against all of the not circled problems. I'm not going to graph it, but if you look, most of the kids with positive numbers are in the online group, and there's a whole lot of negative numbers in the in-person group. So it'd be another way of looking at your data holistically and seeing that maybe there is an advantage to being in the online group. Okay, so this slide right here, a little bit more above and beyond, just a different way of approaching it, but looking at things within blocks like we started off on these slides, very, very important. So let me go ahead and proceed here. So I've said a few of these things already, but this is good just to be able to talk about it again and have it here in your notes. Blocking in experiments is similar to stratified sampling. I've already talked about that and the difference. You can backpedal in this video and hear me say that again if you need it. But picture it's like stratified is for sampling. Blocking is for experiments. So blocking is a form of random, or blocking goes well with random assignments. Stratified goes well with random sampling. And then blocking is a good way to increase your chances of finding convincing evidence. We've talked about that. It was easier to see there was a difference when we compare apples to apples. Blocks should be chosen like strata. Units within the block should be similar and different than the other blocks. This line right here is important. You should only block when you expect that the blocking variable is associated with the response variable. Okay? So in my same problem with my online class, my in-person class, blocking by somebody's hair color would be a stupid thing to do because there's no real incentive, there's no real thought that people with brown hair are going to do differently in online or in person. If you block by a poor choice of a variable, one that doesn't actually influence things like you were thinking, what you've done is you've fragmented your data. Instead of looking at 20 and having a 10 and a 10, if I went by hair color, now I've got 3 people with brown hair, 3 people with brown hair. 3 versus 3 is not as good as 10 versus 10. So if you block poorly by a variable, it doesn't have to be as ridiculous as my example right there. But if you block by something that doesn't actually matter, you run the risk of fragmenting your data too much to find anything meaningful. And blocks are not formed at random. They are chosen in advance by the experimenters. There's one other phrase that's super important. I want you to put a star by it in your notes. I said it out loud earlier, but now it's actually here for you guys. Blocking accounts for a source of variability in your data. The math class you're in is going to be a source of variability in how much you improve. Blocking balances it out and makes sure that you're comparing apples to apples. All right, so something to think about here at the bottom. What are some variables that we can block for in the caffeine experiment that we did? So let's go with our hypothetical one we didn't actually do with the caffeine. So I'm going to give you guys cups of soda. So think about what would be a good choice of a blocking variable, okay? So a couple things we could do here now that you've thought about it. One, probably pretty good one, would be caffeine tolerance. So if I have 10 of you guys who have caffeine a lot and 8 of you guys who don't have caffeine as much, I would take the 10, that'd be my block, and make sure 5 of you get the caffeine, 5 of you get the caffeine free. Then I take my 8 kids who are not big with caffeine and do 4 and 4, and then you compare those little groups instead of comparing the whole big pile. You could say other things like weight, athletic ability, et cetera, et cetera. As an experimenter, what you would do is you would put people into piles based on some variable. You can block by more than one variable, but you fragment your data into too small of groups. So generally, you'll see it just with one variable. And then what you do is you deal out the people into piles randomly. In general, how can we determine which variables might be best for blocking? Just kind of common sense, logic. Maybe if you have prior research in the area, you may know that something is going to influence things. You don't want to just guess something and do blocking just because it's a good idea, because you think it's a good thought. You have to have some motivation and some reason to believe that what you're doing will be helpful. All right. So I believe that this guy right here is my last slide. Let me verify that. Yeah, it is. So we have a fresh context right here, and I'm not going to write this. I'm just going to talk you through it. So we have a popcorn aficionado here, and she has 4 types of popcorn, and she's going to see if the popcorn button on the microwave does better with popping the kernels than using the amount of time printed on the bag. And when she goes to the store, she's going to buy 4 kinds of popcorn. There's movie butter, light butter, natural, kettle corn. 40 bags altogether. Why would randomized design be preferable to a completely randomized design? This I do want to write at least something on, because this is important and something I could very well ask you to do on a quiz. The type of popcorn is likely a major source of variability in how many kernels will pop. Blocking accounts for this variability. Okay. Some types of popcorn probably pop better than other types of popcorn. If you got all sorts of butter wrapped around it, maybe that stops it from popping as well, or whatever. So rather than comparing all 40 bags, 20 versus 20, and maybe I ended up with more of butter in this kind of group right here, you break it up so you get half and half. When you do, like if I would have done just a randomized design with all 40 bags, my results are not going to be biased. And I'm not running the risk of confounding. So those are 2 things students will incorrectly assume sometimes. Your process is still random. So you're not favoring one side over the other consistently, Just in one trial, you may have more in one group than in the other. So your results, if you repeat this, you replicate it multiple times, will have more variability because you could get more butter over here this time and more butter over here the next. So your results are more spread out, and then they're harder to tell if there's overlap for statistical significance. Okay? Outline a randomized block design for this experiment. We've talked about that before. I don't want to write it all out right here, but basically what you would do is you could give me a play-by-play with this. You would start by putting them in groups of 10. So take the 10 movie butter, randomly assign 5, give a number to each one, randomly assign 5 to this group, 5 to this group, blah, blah, blah. Proceed and do the same thing. Repeat the process with light butter, natural, etc. You just talk in words about what you're going to do, making sure you highlight those key things we talked about earlier in the lesson. Very last thing, I didn't want to waste an extra piece of paper. This is the 8th slide, but this is actually important, and it looks not important because I tacked it on the end right here. But put a star by this last definition. Matched pairs design is important, and it's the last thing we have to talk about in our notes right here. Matched pairs design is blocks of size 2 with very similar individuals in each group. So I'm going to give you a few examples of this. Match pairs is a special type of blocking where you have 2 people in each group. And what you do is you take those 2 people and you give one treatment and the other treatment, and then you compare those 2 people. Okay? Very easy example to understand. Say you had identical twins and you wanted to test, some sort of medication. Since they're genetically so similar, you could give one twin one kind of medicine and one twin the other, and compare between the 2 of them how their responses are going to be. Now, naturally, you don't always have identical twins, and that's not even necessary to do a matched pairs. Let's take our SAT example. Let's say I was going to do an SAT study on you guys in class. What I could do, instead of doing a blocking, since you guys are all in the same math class, what I could do is take the 2 people with the highest SAT scores in the class, or ACT scores, and put one in each group randomly. Then the next 2 highest scores, one here, one here. Next 2 highest scores here, here, etc. So you basically are pairing people up who are very similar, and then you're making sure one goes to each treatment. There's also an example in our book. It doesn't even have to be 2 separate people. Let's say I wanted to test 2 kinds of deodorant to see which one works better. I could use myself as a matched pairs and randomly assign one arm, one kind, one arm the other, and compare on myself. So you can even get creative with things like that. But matched pairs even further accounts for variability, because if I'm testing both things on myself, all those other factors about sweat levels, athletic ability, et cetera, are the same. So match pairs is a nice way to account for a lot of the variability. But blocking in general, whether it's regular blocking or matched pairs, basically, in a nutshell, makes it easier to tell if what we are testing is actually statistically significant.